The sun has been a significant solid area for us, especially of late, and it will go through a basic, additionally enchanting change, the inversion of its magnetic field. This connection occurs generally at standard intervals, meaning the midpoint of the solar cycle, and it has expansive repercussions for us here on Earth. In all honesty, it's conceivable that quickly the sun could introduce a serious gamble that could cause total disturbance and disaster for everybody in the world. As you will find, the sun's magnetic field is made by the development of electrically charged gases in its interior, an interaction known as the solar dynamo. Over the long haul, this magnetic field turns out to be progressively eminent and reshaped due to the sun's change and convective changes. In the end, this cycle prompts a total inversion of the attractive poles. The north magnetic pole changes into the south magnetic pole, as well as the other way around. So, might we at any point stall the whole cycle and investigate the sun? The sun is made principally out of hydrogen and helium as plasma, a condition of matter where electrons are not bound to particles, resulting in a combination of free electrons and ions. The sun's interior is separated into several layers, with the core at the center encased by the radiative zone and the convective zone. The core is the sun's most significant region, where atomic fusion happens, converting hydrogen into helium and producing gigantic amounts of energy. Over the core lies the radiative zone, where energy is moved outward by means of radiation. In this space, energy moves slowly outward as photons are absorbed and re-emitted by the solar plasma. The outer layer of the sun's interior is the convective zone, where energy is transported by convection. Blistering plasma rises toward the surface, cools, and sinks again, creating convective flows. The solar dynamo process works fundamentally in the convective zone and the tachocline, a thin layer that lies between the radiative zone and the convective zone. The tachocline is critical since it's where the sun's differential rotation and shear flows play a fundamental role in making the magnetic field. Now, here's something fascinating that you probably haven't heard. The sun doesn't turn as a solid body. Rather, various pieces of the sun rotate at different rates, with the equator turning quicker than the poles, a peculiarity known as differential rotation. This differential rotation stretches and contorts the magnetic field lines, lengthening the magnetic field. The solar cycle is a roughly 11-year cycle during which the sun's magnetic field goes through a progression of changes, finishing in an inversion of its poles. This cycle is driven by the solar dynamo and involves several phases. At the start of the solar cycle, the sun is in a state known as solar minimum, characterized by a low number of sunspots and minimal solar activity. The magnetic field is generally simple and bipolar, with a distinct north and south magnetic pole. As the cycle advances, the number of sunspots increases. Sunspots are regions of intense magnetic activity and are associated with the rise of magnetic activity from the sun's interior. These sunspots appear in pairs with opposite magnetic polarities and migrate toward the equator over time. Around the midpoint of the solar cycle, the sun reaches solar maximum, a time of peak activity with the greatest number of sunspots, solar flares, and coronal mass ejections, CMEs. The magnetic field becomes very complex and tangled due to the continuous twisting and shearing by differential rotation and convection. As solar maximum fades, the magnetic field begins to reconfigure itself. The reshaped and tangled magnetic field lines reconnect, and the global magnetic field gradually switches its polarity. The north magnetic pole becomes the south magnetic pole, and vice versa. This cycle is facilitated by the development and reconfiguration of solar plasma. After the pole inversion, the sun enters a period of declining activity, returning to solar minimum. Eventually, the magnetic field reconfigures, and the cycle is ready to start anew. At present, we're in the solar maximum stage, and the sun's magnetic field is about to flip. During this stage, we can expect to see some activity from the sun that could be as perilous as it is fascinating. However, the sun's magnetic field inversion is not an unexpected flip, but rather a continuous cycle. As the solar cycle progresses, the sun's magnetic field undergoes a series of changes. Right now, the magnetic field is at its most wound and tangled state. It reaches a tipping point and begins to rearrange itself. resulting in a flip. So, do we have any idea when the sun's magnetic field will flip? Researchers monitor the sun's magnetic activity using various instruments and methods. Observatories equipped with powerful telescopes, both on Earth and in space, provide detailed images of the sun's surface and its sunspots. Instruments like the Solar and Heliospheric Observatory and the Solar Dynamics Observatory measure the sun's magnetic field and its changes over time. One key indicator of a looming magnetic inversion is the behavior of sunspots. During solar maximum, sunspots appear more frequently and become more pronounced as they push toward the sun's equator, a sign that the magnetic field is becoming more unstable and is preparing to flip. While we're on the subject, we should dive a little deeper into sunspots. When the sun's magnetic field lines become curved and tangled due to differential rotation, the sun's equator rotates faster than its poles, causing the magnetic lines to stretch and twist. When these lines circle over the sun's surface, they suppress the convective movement of hot plasma from the sun's interior, resulting in the cooler, darker patches we see in sunspot images. Sunspots are captivating solar features, and they can sometimes produce powerful solar flares and coronal mass ejections, CMEs. These phenomena release immense amounts of energy and charged particles into space. When directed toward Earth, they can disrupt satellite communications, influence power grids, and pose dangers to astronauts in space. Additionally, increased solar activity can enhance auroras, but it can also bring radiation spikes in Earth's upper atmosphere. So while we're on the topic, let's examine the difference between solar flares and coronal mass ejections, CMEs. While both are massive eruptions of energy from the sun, they differ significantly. Solar flares are sudden, intense bursts of radiation caused by the release of magnetic energy associated with sunspots. They emit a colossal amount of energy and light, often as X-rays and ultraviolet radiation. Consider them explosions of brilliant light and heat on the sun's surface, akin to a huge blast. Conversely, CMEs are enormous releases of solar wind and magnetic fields from the solar corona. They can be thought of as giant bubbles of gas and magnetic fields being expelled into space. When a coronal mass ejection occurs, it sends billions of tons of solar particles into space at incredibly high velocities. While solar flares and CMEs are connected, they are not the same. A solar flare can happen independently, but sometimes an extraordinarily strong solar flare can be accompanied by a CME, although a solar flare doesn't necessarily cause a CME. They can be linked in terms of risk. Solar flares can disrupt radio communications, navigation transmissions, and pose a significant risk to astronauts in space due to the intense radiation. However, CMEs can have a broader impact. CMEs can cause geomagnetic storms that disrupt power grids, satellite operations, and navigation systems. They can also enhance auroras but present serious risks to Earth's technology and infrastructure. Another consideration is that during times of high solar activity, the amount of high radiation reaching Earth also increases. Satellites and other spacecraft are particularly vulnerable to elevated solar activity. The charged particles from the sun can damage electronic components, disrupt communication transmissions, and even alter satellite orbits. Beyond harming technology and infrastructure, what else can happen to the planet? While the sun's magnetic field inversion doesn't directly influence Earth's atmosphere, the associated changes in solar activity can have an impact. Some studies suggest that variations in solar radiation can affect atmospheric conditions and weather. For instance, increased solar activity can lead to a slight warming of Earth's atmosphere, potentially exacerbating existing climate change. Could auroras be the only positive aspect we experience here on Earth? Perhaps one of the most striking impacts of increased solar activity is the enhancement of these magnificent lights. These natural light shows, known as the northern and southern lights, occur when charged particles from the sun interact with Earth's magnetic field and atmosphere. We often hear about the aurora borealis, but these lights can also be seen around the South Pole. During times of high solar activity, auroras become more frequent and can be visible at lower latitudes, offering dramatic nighttime displays. However, next to the beautiful auroras, there are also more unsettling aspects of the sun's magnetic inversion that could occur if we are ill-prepared. One of the primary risks associated with a magnetic field inversion is the increased likelihood of geomagnetic storms. These storms occur when solar wind, overburdened with charged particles, interacts with Earth's magnetic field. In extreme cases, they can cause widespread power outages and damage infrastructure. One such event occurred on the morning of September 1, 1859. Astronomer Richard Carrington was observing the sun through his telescope, as he had done many times before. However, what he saw on this particular day would stand out in history as the first recorded solar storm. At 11:18 a.m., Carrington saw a brilliant flare of white light radiating from a group of sunspots. This event, now known as the Carrington event, marked the beginning of a new understanding of solar activity and its effects on Earth. The Carrington event produced spectacular auroras that were seen as far south as the Caribbean and caused significant disruptions in telegraph systems across Europe and North America. Some telegraph operators reported sparks flying from their equipment, while others were able to send messages even without batteries due to the induced currents from the geomagnetic storm. This incident highlighted the potential impact of solar activity on technology, an awareness that remains crucial today as we rely heavily on electronic systems. In modern times, the stakes are even higher. Our infrastructure is far more interconnected and dependent on satellites, power grids, and communication networks. A similar event could potentially disrupt these systems on a global scale. Today, scientists continue to study the sun's activity and monitor its magnetic field using advanced technology. They aim to predict solar storms and mitigate their effects on Earth. Space weather forecasting has become a vital area of research, helping us prepare for potential disruptions caused by solar flares and CMEs. For instance, the National Oceanic and Atmospheric Administration, NOAA, and NASA work together to provide real-time data on solar activity. They utilize satellites like the Solar Dynamics Observatory and the Advanced Composition Explorer to monitor the sun's output and predict solar weather events. In addition to monitoring, there are also efforts to harden our technology against potential solar storms. Engineers are designing more resilient power grids and developing protocols for satellite operators to follow during periods of heightened solar activity. Furthermore, researchers are exploring the potential effects of solar activity on climate. While the direct impact of solar changes on Earth's climate is still a subject of debate, some studies suggest that variations in solar radiation could influence long-term weather patterns and climate change trends. In conclusion, the sun's magnetic field and its cycles have profound implications for life on Earth. From creating the beautiful auroras that light up our skies to posing significant risks to our technological infrastructure, understanding solar activity is crucial. As we move forward, continued research and preparation will be key in mitigating the impacts of solar storms and harnessing the knowledge we gain from studying our closest star.